Okay, so in this video I want to define the Chow Rings and Chow Groups. They're kind of higher dimensional versions of divisor class groups, so let's just recall some of this. So divisor class groups. So in Picard groups, I just want to recall these things. So X is going to be a scheme, and we're taking div X, and also denoted by Z1 of X, or Z, and then so I'm going to do dimensions, codimensions here, and dimensions in lower subscripts. So this is the dimension of X minus 1 of X. Okay, so this is formal Z linear combos. Combos of integral subschemes. Closed integral subschemes. Okay, so of codimension 1. So this is what we have. So then we define that. So there's this definition, and then we can define P1 of X. So this is going to be the principal divisors. So principal divisors. Divisors. And so this is going to be this is going to be generated, or we'll just say it's going to be the divisors of the form div f, where f is in the function field of x. So let's say that the function field of x makes sense, or we take a component of x, so it does make sense, and then we take this, and then we take the divisors of this. Okay, so then we define. So let me explain what this is. So for f in the function field of x, so div x is equal to the sum of z, and then we have the order of vanishing of z of f times z, and so these guys are in the codimension. So these are codimension 1 subvarieties, subschemes. So let's say integral. Okay, so we have this. Now I need to still define what the order is. Okay, so then we give another definition. Okay, so let's take Z to be a subscheme, closed subscheme of X. Let's say it's integral. So integral, the word integral should have been the word irreducible. Okay, but whatever. I don't know who's responsible for this, but it's a pain in the ass. Okay, so Z is a subscheme of X. So we define the order. Let's take F to be a function, like a rational function on X. And so the order of Z of F is going to be defined to be the length with respect to this O of X module structure. So Z is going to be the generic point of Z of this module here, where we mod out by F. Okay, so this is what we define to be the length. Okay, or sorry, the order. So this is the multiplicity. So the order of vanishing of F along Z. Okay, so that's what we have, and so this allows us to define principal divisors. So note that when X is normal, and Z is codimension 1, so this is like this is a 1 here. So the codimension 1 subvarieties, we get this from the valuation. So this is the same as the valuation. So this is okay. So let me. You know, I said integral was bad, or valuation order. So this is what they do in Hartshorne. Okay, but you know how I said that integral is bad. Normal should have been called integral because this is integrally closed in the sense of solutions of polynomial equations, so univariate polynomial equations. Okay, so that allows us to define this, and so using, okay, so we have this divisor class group, or we have the divisors now. So then we can define the divisor class group of x to be equal to div x modulo p1 of x. Okay, so this is the divisor class group. Okay, so then when say x is smooth, so recall when x is smooth, then we have this isomorphism between pic x, and this is equal to the divisor class group of x, and here this was equal to line bundles on x modulo isomorphism with the tensor product. Okay, and here we can take a divisor and we map it to this sheaf OXD here, where this is the thing where this is functions with poles at worst D. Okay, so this is the this is what this thing is. So this is this sheaf, and so this construction is important. This is the locally free sheaf. So we're gonna again conflate line bundles and locally free sheaves in this talk. Okay, another thing that I want to say is that this relationship here, so this, when we do this, this is called rational equivalence. So modding out by this is called rational equivalence. It's called rational equivalence because you're moving along P1s. Okay, so I defined order, I defined divisors. So I want to do the higher dimension now, and so higher dimensions. Okay, so Zi instead of Z1. So this is going to be formal linear combinations. So Z linear combos of integral subschemes of closed subschemes of codimension I. Okay, and then so once we have this, so these are called the algebraic I cycles. Okay, so that's the definition here. So then, and what we're going to do is we're going to mod these out by certain equivalents called rational equivalents. Again, we have this convention that z of I of x is equal to z of the dimension of x minus I of x. So lower subscripts are for dimensions, and these are codimensions. Okay, so so let me give a definition. So a divisor, actually let's say this. So if f is from y to x is proper, so this is like a closed immersion. So you can think of closed immersion. Then we have a map from z I to of y to z of something of x, and so I don't know what this something is, but what it does is it takes some v, okay, some class here, some algebraic cycle, and it just takes the image of v, because when you're proper, you take closed things to close things, and this is what happens. Okay, so we have this, and so now I can define what principal divisors are, or principal cycles. So these are going to be the image of so there's the span, let's say span of image of divisors on codimension I minus 1 subvarieties or subschemes. Okay, So integral subschemes again. So the idea is we need to define the notion of principal divisor. So what we'll do is we'll kind of find a subvariety that we can use the notion of principal divisor on, and then we we use those as to mod out by. So we just kind of have to move around our subvariety that we're doing this on. Okay, so we have this, and now I can define. I can finally define the so the image here, the image of these things. So we have like a codimension 1 thing. So we have like y, it's sitting in x, and so this is a proper map, and so we have an I star from ay, or sorry, from z1y to z. So let's say z. Okay, so this is the dimension of y minus 1. So this is the dimension of y minus 1 is equal to m. Okay, sorry for this being messy. And then this thing goes to m minus 1, the same thing, of x. So the dimension stays the same. Okay, of x. Okay, so this is what I meant by the image of these things. Okay. That being said, we can now say that we can define ai of x is defined to be equal to ci of x mod pi of x. And so this is equal to the ith Chow group of x. All right. So we have the definition of a Chow group. So this relationship here is sometimes called rational equivalence. And so this generalizes the idea. So this is like the higher dimensional divisor class group. A divisor class group. Okay. So we have the higher dimensional divisor class group. This is great. So let me say some of the properties that it has. Okay, so where are my notes? That's not what I want. One second. So I have my notes. They're here. They're just a little messy. Okay. So let me say some facts. So first, this is the Chow group. So we can make it into a ring. So the Chow ring, we can make this is this guy, and so the multiplication goes from a of I cross a of j to a of I plus j, and what we do is we define x times y to be equal to the sum, and now we're going to have to use this notion of intersection multiplicity that we defined in a previous video, and it turns out that this is well defined. I of z of xy times z. Okay, so this is the intersection multiplicity. Okay, so we have this Chow group, and now we have this Chow ring, and this is well defined. So it's a fact that this is well defined. So given this, so so facts, some more facts. So this thing takes schemes, and what it does is it gives us a graded ring, and this is functorial. Is functorial. It's a contravariant functor. So if we have a map f from x to y, we get a natural map from a of y to a of x. So we shouldn't worry about thinking about these properties too much, because I'm going to define in a second an abstract version of the Chow ring, which kind of encapsulates all these properties. So here you just kind of take the inverse image of cycles, and then this is what will be well defined. So another thing is if so this is the category. So this is just all morphisms. If you take the category of schemes with proper morphisms, then we get another functor. If f of x to y is proper, then we get a lower star map. And so what we do is we take a cycle here. So I'm going to define it on a single cycle, and we take f of v. This is closed again. We take it in here. The other property is so for two classes, alpha in a of x, beta in a of y, and f x to y proper, we have this kind of projection formula. And it says that it's kind of linear. It's kind of almost linear. Alpha. So if I have this pullback map, okay, and I can pull back a class and multiply it here. Well, these two things destroy each other, and it distributes. So this is equal to alpha times f of beta. Okay, so this is what the projection formula says. It's kind of interesting to compare this to the Frobenius and Verschiebung in characteristic P, or for Witt vectors. And this is not accident. Okay, so let me define this in the abstract sense. Okay, so abstractly, this is how Grothendieck does it. So this is in his Chern class papers. Okay, so now we're going to do it again. So we're going to take SP, so this is going to be a category of spaces. So we need notions like closed and things like this. So we can think of the category of schemes here again, and then we need for this space to have we need to have it to have physical projective bundles. So this needs for x in space, and then E a vector bundle on x. We need the projective bundle of E to be an actual space. It needs to be representable, and so this needs to be an element of space. And so this is the bundle, right, that sits over X, where you kind of projectivize all the lines above a point. So you kind of like take the projective bundle at each fiber. Okay, so so the definition now. Okay, so here's what Grothendieck says. So Grothendieck says a Chow functor. So what is a Chow ring? A Chow ring has some data, right? A Chow ring is a functor. Okay, where we take A, and it goes from, say, these spaces to these graded rings. Okay, and it has the pullbacks, so it's a functor, and by functor this has pullbacks. Okay, So and then so then there's also there's this additional data of there's a natural map map. So C1 from the Picard group of X to for every X. So there's a kind of a functorial thing to A1 of X, and and then when we have a proper map, so if X to Y is proper, this is F is proper, we're also going to have a push forward. So it has this thing from the churn class. So and then there's this proper map thing. So let me say, so there's this thing from X to A of Y. Okay, so let me say again what's going on with this the correspondence. So the Picard group and so I should have said this. So let me take a little pause on this definition. So if I didn't say this already, so the Picard group and the divisor class group, the isomorphism here, was given by taking a divisor and mapping it to OX of D here. And so what this thing is going to do is this thing is going to be asking for you to take this for a certain line bundle to its associated divisor. Okay. It's called C subscript 1 because this will end up being the first churn class. And so this is actually the first churn class construction. You take this guy to its divisor. Okay. So, okay, and then there's 4 axioms plus 4 axioms. And then the 4 axioms I'll do on the next page. Okay, so let me get rid of this. 4 axioms. Okay, so the first one is that okay, so this one's kind of weird if you're not used to this, and this will be really important. It says that so for every vector bundle on some scheme X, we have that the Chow Ring of the associated projective bundle is going to be generated by A of X. So there's this pullback map. So P of X goes to here. And so this is going to be an A algebra. And then there's going to be a certain class that it's generated by. And this class is going to be given by the class of the line bundle, the tautological bundle. So this is the tautological bundle. Okay, so this is the bundle associated to this projectivization here. Okay, so this is the bundle. So this guy here is the bundle such that when you push it forward, you get E. So note that here, pushing this forward gives you E. So under the natural projection from P of E to X. Okay. Okay, so this is the first one. 2, and so this is generated. This will have some relations too. This is what. Okay, so that's that. The second thing is that so there's kind of this normalization. So the normalization is the thing that I talked about here. Okay, so this is going to have to do with this normalization again. It says that for every X. And so for every line bundle on X and every section, every global section, H0 of XL, and then what we do is we define D to be equal to the zeros of S, and then what we can define I of D from D, and this is going to be the closed immersion of D into X. Okay, so we have the zeros of S, and we can view it as a closed subscheme. And what this says is that the class that we're constructing is going to be equal to the 0 sections of, okay, so there's an identity map. So this thing here, okay, so this is proper, right? Okay, so since it's proper, where am I? The axioms. So since it's proper, we have this map. Okay? And in particular, this guy will have an identity. So I did Y here, or what did I call it? I called it D. So this is from D to X. And so this thing will have an identity, and when we push it forward, it's saying that this should agree with the first churn class. Well, it's going to be the first churn class of the line bundle. Okay, so the third axiom says that if you have two proper maps, that the composition of the push forward is the push forward of the compositions, or sorry, the composition of the push forwards. So we just have this. So we have two proper maps, and then the fourth one is the projection formula. So that's the thing that we had before. So A4 is this projection formula. This says if we have this proper map, so it takes closed things to close things, that's the way to think about it, times beta is equal to alpha dot f star beta. So this is this kind of linearity with this inverse here. So this like this f star inverse linearity of f lower star. Okay, so that's the way to think about this. Okay, so these are the kind of the important properties that characterize the Chow group. And so when you do it this way, it allows you to kind of play around with what you want this to mean and what you want your Picard group to mean. Whereas what you want your Picard group to mean. Maybe you could do this with relative divisors, things like this. So that being said, I'm going to bring this video to a close. Thanks for watching. If you have some questions, leave some stuff in the comments. Thanks.